Let's now look at row K, which is a list and list operation. In other words, it's operating on two lists to give a list result. And in K1 we have the function positions of LB on LA. We can explain that fairly easily by looking at LB, and the first item of that is 20. And where is that on LA? It's the second item, so we end up with 2 here as a result for that. Where is 35 on the first item, first list? It's not there, so we get 0. Where is 60? It's the fifth item, so we get 5. Where is 10? Well, actually it appears twice. So first time it gives us the position 1. 10 then occurs here again, and this time it will give the next position of 10 on the first list. So it gives us position 7, and we ask it to find position of 20 on it, and it's already found 20 once. There isn't another one, so it gives 0. In K2 we're asking it to find which items are common to both LA and LB. And you can see from the result that the only items that are common are 20 and 10. And it ignores any duplicates. For K3, we're asking for the union. In other words, which items are on both LA or LB. And this time it finds all of those, but it again ignores any duplicates. In K4 we're asking it to sort list LA by LB in ascending order. What that means is we sort the items in LB, and then we look for the corresponding items that are in LA and put those out instead. So if we mentally sort LB, it becomes 1, 2, 3, 3, 5, 6. And so we look to find the corresponding items for 1, first of all, which is the 10. And then the next one, the 2, will be the 20. And then 3 will correspond to 30, first 3. The second 3 will correspond to 60, and so on. The last function I'd like to show on this row is simple map values in K5. And you'll see that LB here, I've sorted them, or I've arranged them in pairs, 2, 45, 5, 55. And what it will do is wherever it finds a 2 in the first box, it will replace it with a 45. Wherever it finds a 5, it will replace it with 55. So we end up with the result 1, 45, 3, 1, 55, 45, 7. The dark green rows, L to N, are all concerned with analysis of a list. Row L, findall, takes 2 lists with items on the second list cycled if it's shorter than the first list, and it simply finds all the items on the first list, A, that satisfy some comparison with the corresponding item on the second list, B. So here we can see we've selected the value of A where A is less than B. And so we look here, is 1 less than 7? Yes it is. Is 4 less than 5? Yes it is. So that appears on the result. Is 2 less than 2? No it isn't. So it doesn't appear. 6 less than 1? No it isn't. And then is 5 less than 8? Yes it is. That appears. And none of the others will appear on that list, on the result list. Just a reminder about item cycling. If the number of items on the second list be less than the number of items on the first one, then those items are cycled or recycled. So in L2 we've only got 1 item, so effectively that's now a whole series of 7s. So it's now going to say what values in A where A is less than 7. So we'll get 1, 4, 2, 6, 5, 6. The rest of them are not less than 7. And we can also, in L3, instead of returning the values of A, we can find their positions. So it's the same as L2, except this time we're looking for the positions of A where A is less than B. So we get position 1, 2, 3, 4, 5, and 8. Row M is concerned with counting the items on the first list, LA, that satisfies some relationship with the items on list B. So in M1 here, I've chosen to find out how many items on LA equal B. So if we look here and see how many items in the first step equal 1, there are none. How many equal 3? There's 1. 5, yes, there's 1. And then we get to 6, there are 2 of them, there and there, and so on. And we repeat. Notice at the end here we've got 6 again, and again it returns the answer 2. In box M2 we've got the same inputs, but we've changed the relationship to be how many items on LA are greater or equal to B, and we see it's 9, 8, 6, 5, 3, and so on. And in M4 we've chosen to look for how many items are not equal to B. So how many are not equal to 1? 9 of them. How many are not equal to 3? 8 of them, and so on. Row N, range selection, selects items from the first list LA, depending on whether or not they are within certain ranges defined by pairs of parameters in the second list. So here we can see we've got the list LA in N1 is 3, 4, 2, 6, 5, 12, 6, 8, 9, 9. And what we're asking it to do there from the drop-down list of functions is to find which values are inside the range 0 to 4 and 8 to 12. And we get 3, 4, 2, 12, 8, 9, 9. So you can see it's left out 6, 5 and 6 because they're not within that range. Secondly, in the second box N2, rather than returning the values, we've asked it to return the positions that those are found in. So we get 1, 2, 3, 6, 8, 9 and 10. And in the third one, N3, we're asking it to find all the values that are outside those ranges. So in this case, the only items it returns are 6, 5 and 6. We now come to the really important if-then-else rows, O to R, all coloured brown. These are all concerned with outputting alternatives depending on a condition or a comparison. The first two inputs are used for the comparison or condition, while the last two are concerned with the alternatives. So there are 4 inputs altogether. Rows O, Q and R all define simple alternative list outputs in their third and fourth input fields. The third input value will be the answer if the comparison succeeds. Otherwise, the answer is the fourth input field. Let's start with the simple if-then-else boxes of row O. Here, the first two inputs are simple numbers, and the comparison is just less than or equals, and so on, up to greater than, between those numbers. So if we specify A to be 6, so we'll actually put some numbers in here, and put 3 as B, and if the two alternative outputs LC is 21, 25 say, and the other one is 9. So what that's saying is if A is less than B, which it isn't, then the answer will be LC, otherwise it's LD. So clearly here the answer is going to be the list 9. If we change B to be 12, so that now A is less than B, then we will get the answer 21, 25. That's the list output. I'm now going to move down to row Q, which is if then else all, and the first two inputs of this are item lists with cycling of the items as we've seen before. So let's put in here 7, 8, 9, and we put in here 3, 10, 11, and we say again that the answer is either going to be 21, 25, that list, or the list with just the number 9 on it. So what this is saying is if all the checks of A being less than B for all the items on the list succeed, then it will be 21, 25. Otherwise the answer will be 9. So again, if we look at this, we'll see that 7 isn't less than 3, therefore it fails, so we get the answer of the list with 9 on it. If we now change item list B to be 8, 10, 11 and press equals, then we get the answer 21, 25, and that's because for each of the checks between A and B, A is less than B. We could also here, because remember this is a recycling list, it will just repeat it if you've got less than the number in the first list. We could make this one 12, and again the answer will be 21, 25, because 7's less than 12, 8's less than 12, 9's less than 12. Moving on to row R, if then else list, the condition is concerned with the relationship between the first two input lists as a whole. Again, let's make the third and fourth inputs 21, 25 and 9. And 9. And if we select the condition to be all LA on LB, so that means that effectively what you're saying there is that LA is a subset of LB, and we make LA to be 4, 5, and we make this to be 1, 2, 3, 4, 5, 6. Then that succeeds because LA is a subset of LB. Alternatively, if we then change this to 4, 5, 7, the answer will be 9 because it's no longer a subset of LB. Now move back to row P, which is an if then else items, in which all 4 inputs are treated as lists of items, with cycling of items on the last 3 to make them the same length as the first. So with this one, the output is constructed from the items on the third and fourth lists, C and D, and the comparison is made between the items on A and B. Essentially, for each set of corresponding items on lists A, B, C and D, if the selected comparison between A and B succeeds, then the corresponding item on the output list will be C, otherwise it will be D. So if we make the list A to 4, 6. The list B to be 5, 2, 6. The list C to be 10, 11, 12. And the list D to be 13, 14, 15. Then remember, this comparison is going to be carried out item by item. So in the first item on the list, is 2 less than 5? Yes, it is. So the answer will be 10. Is the second item 4 less than 2? No, it isn't. Therefore, we'll take an item from second item from D. So that's 14. And is 6 less than 6? No, it isn't. So the answer will be 15. Just to show the idea of cycling again, if we make this just the item list of 5, make this 1. So it's 1 if it succeeds and it's 0 if it doesn't. And we press equals. We get the answer 1, 1, 0 because 2 is less than 5. 4 isn't less than 5, so it's what is less than 5, sorry. And then 6 isn't less than 5, so we get 0. The if then else items functions can be very useful when combining lists of numbers, for example, with graphics. So what I'm going to do now is go up to row E, where I've defined some numbers in here that give me black stripes, black stripe, red stripe, and black stripe again, which I've called red horizontal stripes. And this one is a blue square, that's -5, on a black background. So if we come down to the bottom here, let's just press equals. I've already put in E1 as the input to the animation zone here, and you can see that you get red stripes. I'm now going to put in E2, and you'll see that we get a blue square in the middle of a black background. So how do I go about superimposing the red stripes on top of the blue box? Now you might be tempted to say, well, let's go up to row V and add E1 and E2 together. E1 plus E2. We know the background's black, so that's not going to make much difference to the background. And if we do that and then show the output, then show the input to the animation zone as being V1, we don't get what we might have thought we'd get, and that's because when we add the red and the blue codes together, we get -3 plus -5, which is -8, and that gives us yellow. So not quite what we wanted. So this is where we can use the if then else items boxes. So let's go up here to row P, and we will put in this one, that if, let's say we want to have, if E1 is not equal to 0, in other words it's not black, then we take the elements of E1, otherwise we have E2, we use E2. And if we now make that the input to the animation zone, so if we go down here and make that P2, then we've got what we wanted, which is the red stripes superimposed on the blue box. Let's go back to P, row P again, and just swap those two around. So let's make this, instead of E1 there, we'll call it E2, Call that E2 and that one E1. And now this should give us the reverse. It should give us the blue superimposed on the red. And that's what it does. So that item by item if then else is very good for combining two lists of numbers representing graphics. We'll now move on to tables. There are 3 rows that focus on these, all maroon coloured. But first we need to remind ourselves what we mean by a table, as Numipulator functions can take only numbers and lists as inputs and produce only these as outputs. So in Numipulator, a table input is defined by 2 separate inputs, a list of values LA and the number of columns n cols. So if the result would intuitively be a table, the result is instead just a list of all the numbers taken from the list starting at the top row by row. As a simple example of this, I'm going to put a list of numbers in here laid out as a table just so you can see it, and I'm going to say it's got 4 columns as we've shown it there. Remember, Numipulator will only read that list of numbers as a list, and I'm going to say shift the rows down as the function. Now if you shift the rows down, you'd expect 1, 2, 3, 4 to be the second row, 5, 6, 7, 8 to be the last row, and 9, 10, 11, 12 to come up and be the top row. And that's what you see there. Effectively, those are the numbers that you would get, the list of numbers, if you take them out of that shifted table. If we now change the function to be rotate by 90 degrees, instead of ending up with a 4 column and 3 row table, we should end up with a 3 column 4 row table where the top row is 9, 5, 1. And so if we do that, press equals, that's what we get. 9, 5, 1, 10, 6, 2, 11, 7, 3, and 12, 8, 4. Table functions are very useful with graphics. For example, we can take E1 as the list LA, and we make the number of columns 10, and we leave the function as 90 degrees, so we can press equals there, and it will rotate that. If we go down here and make T1 the input to the animation zone, you can see now that instead of having the horizontal stripes, we've now got vertical stripes. Likewise, if we go up and change the output, the function, to be shift down again, and press equals, now we should see the result graphically, and we can see that those red stripes have been shifted down. Altogether, these table functions allow us to rotate, to flip, to sort rows or columns, to remove duplicate rows or columns, and also to derive results that aren't intuitively tables, such as the number of rows or the sums of all the rows or columns. Table operations are mostly concerned with analyses of a table. They can take several sets of parameters and output sets of answers. You'll get one result for each set of parameters, one after the other. So let's just demonstrate that. If we have LA equals 1, 2, 3, 4, 5, 6, 7, 8, 9, and we say that there are 3 columns as we've shown them there, and say we want row P1, where P1 is either 2, we want 2 and 3. So that's going to give us 4, 5, 6, which is the result for the 2, and then 7, 8, 9 following on. It's important to remember that the results for each set of parameters follow on one from the other. Many of these are intended for multiple sets of parameters, such as row and column, while others would probably only normally be used with one set of parameters, such as delete rows P1 to P2. These operations let you select cells and blocks of cells from a table. They also let you search for rows or columns that contain certain values at a particular position. For example, all rows where the second column contains a value greater than 10, for example. You can also find the sums of certain rows or columns, the number of a particular value found in specified rows or columns, and many more analyses like that. There are also operations concerned with clusters, particularly useful in games or puzzles, that enable you, for example, to find all cells that have the same value as the specified cell, either horizontally or vertically or diagonally. It's also worth noting that there are a group of functions within table operations that allow you to do anything to each row or each column of a table that you would do with a list function, either ending up in a number or a list. So for example, you might say, I want to have a permutation of each row of the table independently, and you can do that. Now going to look at the third row table construction, row U, which is concerned with taking an input table and producing an output table by changing parts of the table, extending it, or maybe merging it with another one. Of particular use with graphics are the cell change functions that let you change the values of individual cells or of blocks of cells. In both cases, multiple sets of parameters can be specified, and unlike the table operations, only one output table is produced, with all the specified changes made one after the other, so that one change may effectively be replaced by another. I've just come up to row G, and in G1 I'm generating 100 zeros, and I'm now going to put that as the LA G1, make that the input to G1. We'll say there are 10 columns, and we're going to put in here the parameters 2, 2, 3, 4, 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. What this means is that we want to replace the items that are in G1, starting at the cell row 2, column 2, and have a block which is 3 rows high and 4 columns wide, and replace whatever's there at the moment with the values 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. Now there's also another parameter here, or another input called D. I'm not going to explain that at the moment. Please accept that you need to put a 0 in there, and we'll say change the block values, and you should start to see there those numbers 3, 4, 5, 6 appearing. Now if we now go down here and put U1 as the input here, we can see that's what we get. We get 3 is red, 4 is green, 5 is blue, 6 is magenta, and we've got those colors or those numbers inserted into that that block of the table. If we now go back and add in another set of parameters for LC, so we've already got that set of changes. Let's just move down a bit and say we now want to add in, starting at cell 4, and height 2 cells and width 3 cells, so that's 6 cells in total, and specify the values of these to be 1, 1, 1, 1, 1, 1, 1. There's our 6 values. And now we press equals. We can see there are our 6 ones, which are white, and they have partially overwritten the changes that we'd made with the color, the initial colors. There are also operations to insert blocks of a single value, both for rectangles, circles and lines, and also the edges of circles or blocks of a certain color. So let's try and do that. So if we go up here, and again we get G1, and it's going to have 10 columns, and we might want to fill in the edge of a block, and we want it to be color yellow. Let's say 8, so yellow, which is 8, so we might say we want a block from 2 to 5 columns deep, 6 columns wide, and we want the color to be 8. We again need to put a 0 in here, and we'll come down here and make U2 the input to the animation zone. And there we have a box edged along the edge with yellow blocks. We're now going to use the table construction functions to create the flag of Switzerland. And we're going to start off by going to G1, and instead of having it generating 100 zeros, we're going to have it generating 100 threes, which you may remember is red, and that's the background of the Swiss flag. We now go back down to here. We still leave G1 as the input. 10 is the number of columns, but we're going to change this. We're going to change the function to be fill block values, because we want everything to be white in this. So we're going to start off with the vertical stripe of the cross and say, so starting at row 3, column 5, we're going to have it 6 cells high and 2 columns wide, 2 cells wide, and it's going to be white. So that's vertical. And then we'll have from 5, 3, we'll have it to be 2 cells deep and 6 cells high, and again it's going to be white. That's going to be a horizontal one. And now we can come down here and make U1 our input, and there's a sort of flag of Switzerland. Now there's a deliberate error here. All the cells have borders, which we don't really want on that flag. So you may remember that we defined the input D in U1 to be 0. So we come up here. If we change this to -1, or in fact any negative value, then all the results of U1 will be multiplied by -1. They'll all become negative. So now if we come down here and press equals, now we get a better looking flag of Switzerland. To be honest, I think you're rarely going to need to change that value of D. Normally just leave it as 0 and do any calculations you may need separately. It's just to show you that it does have some sort of meaning.